Okay, let's talk about number 31 from Segel. So these questions uh, ask you about the pH of a solution that obtained from the mixture between 400 mL of 0.2 molar sodium hydroxide and 150 mL of 0.1 molar H3PO4. So this mixture is the mixture between the acid and the base, right? So it's weak acid and strong base. So every time you mix acid and base together, you're gonna form two products. So in this case, acid H3PO4 plus sodium hydroxide. The first product is the salt. In this case is sodium phosphate. And the second product is always water. So before we calculation the pH of these mixtures, you need to keep in mind that and make sure that this reaction equation is balanced. So first, you need to balance these equations by putting 3 here and then 3 water here. So now the equation is balanced. The approach for these equations is to use the I table again. So for the amount that you put into the table, make sure that all of them is consistent in unit. For example, in this case, I'm gonna use moles of either sodium hydroxide and H3PO4. So for sodium hydroxide, moles of sodium hydroxide will be equal the volume times by the molarity. This is equal 0.08 moles. So every time you calculate moles, make sure that the unit is consistent, right? And mole for H3PO4 equal 0.15 liters times by 0.1 molar, and this is 0.015 moles. So now you can put the moles in the tables. So H3PO4 is starting with 0.015, and then sodium hydroxide you're starting with 0.08. Okay, so when you let the reaction begin, one of the substrate will be limited. And in this case, the one that is being limited is H3PO4. So if you notice here, H3PO4, you just have only 0.015, and one equivalent of H3PO4 needs to react with 3 equivalents of NaOH. So if the H3PO4 is a limiting substance here, it means that it needs to react with 3 times by 0.015 moles of sodium hydroxide. And that is equal 0.045. So now we know the amount that being changed during the reaction. For the product part, you would form 0.015 moles of Na3PO4 too. So at equilibrium, you get rid of all the H3PO4, but sodium hydroxide is being left 0.035, and you have sodium phosphate 0.015 moles being formed. So let's talk about sodium phosphates here. So because it is the salt, and when it's in the water, it will associate into sodium ion and phosphate ion. And comparing phosphates here and NaOH, so the NaOH is far more stronger than the phosphate acid. So in this case, we can calculate the pH of the solution at equilibrium by just focusing on the sodium hydroxide part, and because it's the base, so you have to first calculate pOH from sodium hydroxide. So pOH, you can use minus log OH in directly, and then you get the pOH equal so the problem is we need the concentration of hydroxide ion here, but this value is actually moles, right? So you need to divide moles by the volume of the solution. So the mole is 0.035, and the volume of the solutions, how can you calculate it? So it's actually the total volume of sodium hydroxide and H3PO4 that you mix in the first place. So in total here you have 550 milliliters, that is equal to 0.55. Okay, so you have to divide by 0.55 liters over here to make it be the concentration. So you get minus log 0.063. And the pOH will be equal 1.19. Again, when you calculate pOH, you can calculate pH using 14 minus 1.19, and this is equal 12.81 here. And when you get the pH, you can also calculate the concentration of proton by take the anti-log of the pH. So in this case, is so the concentration of proton can be calculated by 10 to the minus of the pH, which is 12.81 here. So that is the answer.